So hey guys, welcome back to the channel. This is your physics buddy. In the recent classes, we started electricity and magnetism and did few lectures on it. We talked about electric charges, we talked about forces, we talked about field. We also talked about field due to dipole. In this session, we are talking about torque on the dipole placed in a uniform electric field. We will be looking at the derivation part and we will be referring the book as per suggested by the different universities. This lesson is going to be very important. Apart from this, different units from AP Physics 2 curriculum has already been uploaded on the channel. You can just check the videos out. Whenever we are learning something new, it takes time. It takes time to understand and it also requires hard work. So just don't see the video. Make sure you write each and everything down and let's get started.
We'll see some of the topics from the book and how all those things were given in the book. We'll refer few of them as well. So basically today we have to talk about torque, but how much torque an electric dipole actually experience when it is placed in uniform electric field. So here are the few formulas. First of all, this is the relation between force, dipole, electric field and the distance. So an important formula, you might be using it in some of the problems. Then we have a formula for torque. The torque is generally given by P cross E, where this cross can be written as P E sine theta. So this is another relation. We are going to prove this in today's session. Then there is another relation for potential energy. So you might see some problems based upon this relation. So potential energy for electric dipole when it is placed in uniform electric field is given by negative of Pe cos theta, where cos theta is the angle made by the dipole with the uniform electric field. So in some of the questions you might be using it or might not be. Let's when we are looking at the book, we'll get to know more about it. So let us try to prove that how torque comes out to be P cross E. So in order to do that, first of all, we have to assume that there is a dipole and that dipole is placed at some angle theta with the uniform electric field. Now, as we already know, when these charges are placed in uniform electric field, they will experience some force. So what is the direction of force? The force will be acting on both the charges in such a way that positive will get attract with the field and it will start moving with the field as it feels force in the direction of field only, whereas the negative charge feels the force in the opposite direction. As you can see here, this negative charge will feel the force in the opposite direction, and that force is something which is called, which can be written as QE. Whereas the positive charge will feel the force in the direction of electric field. So this direction of electric field, now you can just observe here that these forces will actually trying to rotate this whole dipole or the configuration of the dipole. So when the dipole gets rotated through an angle theta, we can say in that case it must have experienced some torque. So let us just try to recall what torque is. So torque is basically the turning effect which is experienced by any object. And this is something which you might have learned in honors physics earlier, let's say in 10th period, as you told me. So torque is basically given by force times perpendicular distance. So whatever force is acting in the system times the perpendicular distance from the axis of rotation will actually give us torque. So in this case, the force which is acting here is QE. Whereas if we talk about the perpendicular distance, so this is going to be the perpendicular distance. As we know, the direction, the length of the dipole, we have already assumed 2a. So this 2a must have component in this perpendicular direction, which is given by 2a sine theta. So this is actually the perpendicular distance we are going to use in this particular relation. So this perpendicular distance can be written as r perpendicular, and when we substitute the value, we'll get 2a sine theta. So here we already know that q times 2a is nothing but the dipole moment. So when we solve this, we got P E sine theta. And whenever there is sine theta, there is cross product. So we get P cross E. We can write it as P cross E. This is the vector form of actually writing torque. So this is a very basic derivation. And through this derivation, we can simply see that how torque comes out to be P cross E. Again, if you have to find out the direction of P cross E, we'll use our right hand. So right hand thumb rule will give us the direction of this torque. And this is also something which we have already studied in previous grades as well. You must have done vectors, and when we were talking about vectors, we actually talk about how the direction of cross product is actually calculated. So this is the simplest proof of torque, and again, it's important to remember this particular relation. So here you can see that the distance between them is something 2a sine theta. Now, let us try to answer this particular question. So the question says in uniform electric field, torque will be. So in uniform electric field, torque can be zero or torque cannot be zero. So in which case torque can be zero and in which case torque cannot be zero? Let us try to understand it. Suppose when we saw that a dipole is placed in this way with a uniform electric field, both the charges will experience force in opposite direction. And when they experience force in opposite direction, they are tends to rotate as the force is acting in opposite direction. And these two forces, which are equal in magnitude but opposite in direction, are sometimes referred as couple. But what is the situation when you place a dipole parallel to the direction of electric field like that? So electric field must be uniform. Uniform electric field means it is constant throughout the space. Similarly, these two charges will experience force, but here the force have no tendency to rotate the whole dipole. So rotation is not observed here. So if rotation is not observed, in this case we can say that the torque is going to be zero. But in this case, torque is going to be P cross E. So this is what you have to remember. In uniform electric field, torque may be or may not be zero. It depends upon the configuration or it depends upon how we have placed the electric dipole. Let's move ahead. So this is one such question where we have to actually find out the maximum torque on the dipole. So the question says that there is an electric dipole consisting of two opposite charges of 2 times 10 to the power minus 6 coulombs, each separated by a distance of 3 centimeter, and they are placed in uniform electric field of 2 times 10 to the power 5 newtons per coulomb. The question says what is the maximum torque acting on the system. So in order to torque to act to its maximum value, let us try to first of all observe what is the formula for torque. So torque is P cross E. This P cross E can also be written as P is sine theta. So when this torque is going to be maximum, this torque is going to be maximum when the angle, that is the theta, is going to be maximum. And for sine theta to be maximum, it can have its maximum value as 1. So here we can say that theta must be 90 degrees, and in that case, torque is going to act as a maximum. So let us just substitute all the values from the given question. So we can write this P E sine 90. Dipole is written as Q times 2A times E. Sin theta is 1, so we can just ignore it. So charge is given as 2 into 10 to the power minus 6. The distance between the charges is 3 centimeters. So we have given the value of 2A, complete 2A as 3 centimeters. So we can write it as 3 times 10 to the power minus 2 into electric field. So electric field is going to be 2 into 10 to the power 5. Or everything is given here in this question only. The 2 3s are 6, 6 times 2 is 12. Similarly, if we just solve it, we get minus 6 minus 2 minus 8 plus 5. 10 to the power minus 3. You're going to have this particular number. So it's quite clear that torque is going to be 12 into 10 to the power minus 3 Newton meters. So option C is going to be the correct one. What you have to understand here is that how you actually substitute all the values and answer everything here. So as so far this unit is concerned, we are left with one particular topic which is called Gauss theorem. We were actually talking about. So let us try to see what is the learning path and how many topics we have covered so far from this particular book. So we have covered electric charge, we talked about types of charges, we talked about conservation of charge, we also talked about charge force law, which is called Coulomb's law. So we talked about these things. Then we talked about electrostatic charging. So electrostatic charging is because of conduction, friction, induction, and there is one more you can say method of charging is given, which is called polarization. So we haven't actually discussed polarization, but here you can assume the polarization simply deals with, suppose you have a conductor and you just place that conductor in some external field. So because of that external field, that conductor which are having some charge, positive or negative, those positive negative charge will automatically align themselves according to the direction of electric field. So we'll review this from this book only, so you'll be able to understand it. Then we talked about Coulomb's law, we talked about forces and charged particle, discussed each and everything quite in detail. Then we talked about electric field, we talked about its direction, its magnitude. We also talked about superposition principle, and then we talked about dipoles and parallel plates. So this parallel plate thing is something which is missing. We haven't discussed it yet. So we'll again review it through this book only. Next, it had conductors and electric fields. So we talked about interior field, surface field, and surface charge density. So again, this surface charge density, we haven't discussed it yet. And this is directly linked with the Gauss law for electric field. So which is the last topic of this particular chapter. So let's review few things from this book and we are good to go. So initially it's, you can say the introduction part, then it's given electric charge, what is electric charge, how it can be described, then we have given here it has been given a hydrogen atom which explains that the proton inside the nucleus which is responsible for the positive charge, whereas the electron which is revolving in the orbit, it is supposed to be representing negative charge. Similarly, if it is beryllium atom, so it must have few more electrons, it must have few more protons, and all the electrons and protons must be revolving. All the electrons must be revolving in the outer orbits, and protons must be inside the nucleus. Like mass, electric charge is a fundamental property of matter, as we already discussed. Also, we have discussed this particular thing, and if not, let's try to understand it. Conservation principles are only defined for mass, energy, and charge. And we also understood that how these all physical quantities are interrelated. So, mass and energy are interrelated as well as charge. If a body possesses mass, it must possess some charge. And if a body possesses some mass, it must possess some energy as well. And that mass and energy can be represented or can be equated using Einstein energy mass equivalence, which is given by E is equals to mc square. So this is the relation which actually relates mass and energy. So these all of these three things are interrelated. That's why they are referred as fundamental property of matter. So does the electric charge. So we discussed all of these things. We also talked about the electric force or isolated charge particle are given by law of charges or charge force law. Basically, positive or the similar charge will repel, whereas the opposite will attract. So here there is given the values of electron, that what is the charge of electron, what is the charge of proton. Also, it has given the mass of electron, mass of proton, mass of neutron. So these are important values and we need to remember them. Sometimes these values are not given in the question. So you have to use these values to answer the question or to solve the problem. So that is something we need to remember. Then here we simply talked about what is the unit of charge. It is supposed to be coulomb. We talked about the attraction repulsion between the net positive and negative charges, similar charges. Then we talked about few more units of charges. One is microcoulomb, another is nanocoulomb. Then we also can have picocoulombs. Microcoulombs is 10 to the power minus, microcoulomb is 10 to the power minus 6 coulomb, nanocoulomb is 10 to the power minus 9 coulomb, and picocoulomb is 10 to the power minus 12 coulombs. Then we talked about this quantization principle where the net charge of any given body can be calculated by number of charged particles, that is number of electrons times charge of electron. So this will ultimately give us the total charge of the body, can be charge of proton and can be a charge of electron, which is going to be similar if we are having same number of electrons and protons in a given body. So this is how we got quantization principle. The charge is quantized, which is we have already studied and understood. Then it says the conservation of charge. Then there is an example 15.1 where the question says, when you shuffle across a carpeted floor on a dry day, the carpet requires a net positive charge. Will you have a deficiency or an excess of electrons? So if it has a positive charge, if it is acquire a positive charge, so here we can say it must have lose some electrons, because when something loses electrons, in that case only it is going to have positive charge. So the answer of this question will be it will have a deficiency of charge. So the next part of the question says the charge of the carpet acquired has a magnitude of 2.15 nanocoulomb. How many electrons were transferred? So how many electrons were transferred? We can simply calculate using Q is equals to NE. Total charge is given. Charge of electron we already know. So we can simply divide the total charge by charge of electron in order to get the number of electrons, which is given here. As you can see here, how it is actually calculated. So 3.1.34 times 10 to the power 10 electrons will be transferred in order to acquire a positive charge of 2.15 nanocoulombs. So a very basic example. We have done some most of them in the class as well. Then there is a method of electrostatic charging. So here there are few methods through which we have actually understood that how a given matter can be made charged object. So in order to understand, first of all, we have categorized matter in three categories. The first is conductor, another is semiconductor, then we have insulators. So here you can see the order of conductivity. So here the silver supposed to have the maximum relative conductivity, whereas carbon in the given set of conductors have the least conductivity. So if we just try to understand that where we actually saw carbon as a conductor, so we can just imagine using a graphite there in the pencil, which can be used to conduct current. And that is something which we must have done in the earlier classes as well through experiments where we actually understood how current is being transferred through graphite, or you can say the lead of those pencils. Then there is another category called semiconductors. So in semiconductors, we generally have two, germanium and silicon, and the order of conductivity is again decreased. So for conductors, it is 10 to the power 7. For semiconductors, it is ranging from 10 to the power 3 to 10 to the power minus 9. Whereas if we talk about insulators, they do not conduct electricity at all. And the order of conductivity is also in negative. So they have a lot of resistance, so they won't allow current to pass through them. So then we talked about electroscope in order to actually understand which type of charge is being there on a given body. So we already understood what electroscope does. So basically a neutral electroscope has charge evenly distributed. So leaves are vertical. They are not separated enough. Similarly, if you brought a negatively charged rod or a positively charged rod, these leaves will separate by few centimeters, and this shows the presence of charge in a given object which we have brought closer to the electroscope bulb. That is again something which we have already discussed and you need to remember. So electroscope can be used to determine whether an object is electrically charged. When a charged object is brought near the bulb, the leaf moves away from the metal piece. So might be question came to your test tomorrow. So there is a method called charging by friction. So in charging by friction, we actually rubbed one object over the surface of another object, and due to friction, some charge may get transferred from one object to another. For example, if a hard rubber rod is rubbed with fur, the rubber will acquire a net negative charge. Rubbing a glass rod with silk will give the glass a net positive charge. So this process is called charging by friction. So again, you need to remember these examples. Make sure you remember how these particular examples are being used. Understood?
Yes, sir.
Then we have another process in which we show charging by conduction. And this is the process in which there is a physical contact between the two charged bodies. As we have already discussed, this particular type of method of charging. Here, one object is brought in physical contact with the another object. The first object must have some charge, then only it is capable of transferring some charge to the another object. So in that case, when they just physically touch each other, so some charge, or you can say the half of the charge which the body possessed initially, will transfer to the another object which is being brought in contact with it. So conduction in this case is refers to the flow of charge during the short period of time the electrons are transferred. So that is something you can remember there. Whereas if a negatively charged rod is brought close to the negatively charged electroscope, a leaf will diverge even further as more electrons are repelled down from the bulb. Here you can see it. If negatively charged rod is brought near electroscope having already some negative charge, so these leaves will went far away from each other. Whereas if a positively charged rod is brought, what will happen? Positive and negative will attract and they will become closer to each other. Another process of charging is charging by induction. So we already understood how the charging by induction works. In order to use this charging by induction process to make a body charged, we use one such process called earthing. So that is something which is important. So starting with an uncharged electroscope, you touch the bulb with a finger, which grounds the electroscope, that is, provides a path by which electrons can escape from the bulb to the ground. So whatever example I gave you in the class, it's better that you should remember that example instead of this electroscope example. So there is a conductor which has no charge initially, or you can say the net charge is supposed to be zero. So when you brought a rod, maybe of positive charge or maybe of negative charge closer to this net charge zero object. So what will happen here is this positive will repel the positive charges present on this sphere and negative will come closer to this rod. What will happen here in this case is if we earth the one side of the sphere like that, so all the positive charge will get transferred to the earth. And when this rod is removed, this whole sphere will become negatively charged. So this is called process of charging by induction. So you can remember this particular example to answer it. Now, charge separation by polarization. So this is not something we have already talked. Let's talk about it a little. So what happens here is suppose you have a balloon which is supposed to carry some negative charge. So what will happen here is this balloon will try to stick to the wall if this wall has any sort of charge. And we can assume that initially the net charge of the wall is supposed to be zero. So the net charge is supposed to be zero, and we brought a negatively charged balloon to this wall. What will happen? The negative charge will push the negative charge away on the other surface, whereas the positive will come closer to it. And in that way, the balloon get stick to the wall without any issue. So this is only possible if the balloon was initially charged. If it was not initially charged, it is not possible. So here, what we have done is we have actually polarized the whole system. So that polarization is ultimately responsible for making an uncharged body a charged body. And here, the uncharged body is supposed to be the wall. Now, electric force, or you can say Coulomb's law. So we already studied all the things related to the Coulomb's law. We studied that Coulomb's law is something which gives the force that exists between the two charges. So the two charges separated by a distance r. So the electrostatic force which acts between the two charges is supposed to be given by k q1 q2 by r square, where the k is approximately 9 into 10 to the power 9 Newton per Newton meter square per Coulomb square, where this electrostatic force depends upon the medium as well. And we already discussed how the medium affects the force acting between the bodies. So if there's a medium, we must have some value of epsilon m, and we already discussed how it is used to actually find out force in another medium. We also talked about this particular thing that if there are two charges of same nature, so whatever force this q1 will experience due to this q1 in this direction towards left, the same force will be experienced by this q2 charge in the opposite direction. And this also proves that F21 is equals to negative of F21, which is there because of Newton's third law. Every action has an equal and opposite reaction. Similarly, if there is a configuration of three charges, and these three charges are separated like that, or maybe drawn like that. So if I try to find out the net force on any of the given charges, so we have to understand this fact that all the charge will experience equal forces. But if we try to find out the net force on any of the given charges, we have to simply understand that positive will repel. So if q1 and q2 are positive, so they will repel each other. So the q1 will experience force in this direction, which is represented by this particular vector. So it can be written as force on 1 due to 2, which is given by k q1 q2 by r2 square. Whereas if we have to find out the force experienced by this q1 charge due to this q3, it is going to act in this direction. And this is something which you can write as F13. So F13 is given by k q1 q3 over r3 square. So in order to find out the net force experienced by this q1 charge, we have to vectorially add these two forces, which is given by F net, which is equals to F12 plus F13. Now this is something which involves vector addition, and vector addition is done by parallelogram law of vector addition, where the net resultant is given by a square plus b square plus 2ab cos theta. So we have to remember this particular relation as well in order to find out net force experienced by any given charge. Similarly, there are a few examples. So let us see this example. This example says it's a conceptual one. So the question says a rubber comb combed through dry hairs can acquire a net negative charge. So when we comb our hairs, that comb might acquire some negative charge. That comb will then attract small pieces of uncharged paper. This would seem to violate Coulomb's force law. Since the paper has no net charge, you might expect there to be no electric force in it. Which charging mechanism, conduction, friction, or polarization explains this phenomena? And how does it explain it? So let us try to understand it first. Okay. So as I was saying, if this paper has net charge 0, it doesn't mean it has no charge. It simply means it has equal positive and equal negative charge. It means when we just brought this paper close to this comb, negatively charged comb, this negative charge will actually repel the negative charges present on this paper to this direction, and positive will get attracted towards the comb. And due to this, this negative will go away and positive will get attracted towards it. So what was the process? Which process actually does this? Tell me. Which method actually responsible for this? Conduction,
Electrostatic.
friction, polarization. Which one?
I think it should be polarization.
It should be polarization. Also, friction plays a major role here when we are charging this comb, because comb acquires charge while we are combing because of the friction, whereas the paper get attracted towards this comb because of polarization. So both of these works equally here, and we need to understand that how it actually happens. Then Coulomb's law, vector addition involving trigonometry. There is another example. We have done these type of questions in the class as well, and I expect that you try to solve some of these questions from this book as well as from the assignment which we have got from the school. This is quite important. So let me just try to give you the hint about this particular question. So basically, the question says that it is shown in the figure. So we have to take care of this figure as well. So this figure is supposed to be given in the question as per this example. But sometimes the figure might not be there. So if the figure might not be there, it doesn't mean we cannot draw it. So you have to understand how charges are being placed. So question says that the 2 point charges minus 1 nanocoulomb and plus 2 nanocoulombs are separated by a distance of 30 centimeter. And question says what is the electric force on each particle. A configuration of three charges is shown here. What is the net electric force on Q3? So this is my Q3 charge, this is my Q1, this is my Q2. So they are separated by a distance of 0.3 meters. So if they are separated by a distance 0.3 meters, the figure says something else. Q1 and Q3 are separated by 0.6 meters, because the distance between them will be twice of 0.3. You have to understand it from the coordinate that is already given in the question. Similarly, it has coordinate 0.4, so this distance is going to be 0.4. But we have to find this R31 and R32. So in order to find out this, it is coming out to be 0.5 meters. By using Pythagoras theorem, I can directly find it out as 0.5 meters. So this Q3 will experience force, so positive will repel, so it will experience force in this direction, whereas this Q2 is positive again, so it will again experience force in opposite direction, that is this. So it is already mentioned here, but in order to find out this angle, because this angle is necessary to find out the net force, so this angle can be find out using trigonometry. As you know that this is 3, this is 4, this is 5, so this angle is something of 37 degrees. You can remember this relation. This is important triangle in trigonometry as well as in math and physics. So whenever you say you see a triangle in which 3, 4, 5 is there, so angle is must be 37 degrees, and the 37-degree value can also be remembered easily. So 37 and 37 will ultimately give us what? 60, 74 degrees. So angle between the two forces is supposed to be 74 degrees. Although you can use calculator to find out the net force. So here you can see F12 and F21 are going to be same. So net force is going to be 0.2 microcoulombs. Similarly, F32 is going to be 0.27 microcoulombs. I already told you angle is going to be 37 degrees. So some of these two angles are going to be 74. You can use either 74 or you can actually just use 37 degree to find out. Like see, there are two forces. They are acting at 37 degrees. So this force as well as this force both have component along x-axis. So this force will have component like that. This force must have component like that. And both the components are going to be cos component. So that is why the F3 is given by twice of F31x, which is supposed to be twice of F32 cos theta. And cos theta is cos 37. So it will come out to be 0.43 microcoulombs. As you have already this leverage of using calculator, so you can use the calculator to find out the answers directly. Did you understand this part, that how you're supposed to solve this particular question?
Yeah, pretty much. I think so.
Yeah, so what's important is that you need to try this after the class. Try this question, solve this question on your own. If you just stuck somewhere, look at the solution, but once try it on your own. Don't look
Okay.
at the solution, try it out. This is kind of important. Now there is some more information based questions. Inside the nucleus, there is repulsive electric force. You can try these questions out. Again, they uses the same relation. Always remember, if there is a force, whatever force is there, this force is actually capable of moving an object. In this case, the objects are charged particles. So it is capable of moving charged particle. And not only moving, it can capable of accelerating a charged particle. It can actually give acceleration to a charged particle. So from Newton's second law, we know force is nothing but product of mass and acceleration. So we have to find acceleration of any charged particle into given force. We can simply find acceleration by dividing force by mass. And this is what is being asked in this particular question. So try to solve that example. Example 15.5, inside atom, electric force versus gravitational force. So this is something I guess we just have to compare what is the electrostatic force and what is the gravitational force and which one is greater. Always remember, there are fundamental forces in nature, and these fundamental forces are gravitational force, then we have electrostatic force, or you can say electromagnetic force, then we have weak nuclear force, last strong nuclear force. So these forces are the fundamental forces that exist in nature. All other forces are actually being derived from these forces only. And as I have written, the gravitational force at the top, it's simply representing that it has the least strength, whereas the strong nuclear force are the strongest force that are existing in this universe. So if the question says which is more, gravitational or electric force, so electric force is going to be much more. You can just compare by actually comparing the value of their constant. K is supposed to be 9 times 10 to the power 9, where G is supposed to be 6.67 into 10 to the power minus 11. So now you can easily see the difference between the values of these two constants. This proportionality constant K in electrostatic force as well as the gravitational constant K, gravitational constant G in gravitational force. So ultimately, what you will figure it out after solving this particular problem by finding out the ratio, that the ratio of electrostatic force to the gravitational force is supposed to be 10 to the power 29. So this is the result. You can also remember this result. Gravitational force is 10 to the power 39 times weaker than the electrostatic force or Coulomb's force. So this is what this problem suggests actually. And this is what we actually have to understand from this particular problem. Did you understand it?
Yeah, most of it, sir.
Then we talked about electric field. We understood that how electric field actually acts. If there is a positive charge, electric field will be coming out of it, whereas if there is a negative charge, electric field will be coming towards it. Electric field can simply be calculated or simply be written as force experienced per unit charge. So whatever force a charged particle will experience, that is something which is represented by electric field. So electric field is nothing but force by charge. When we solve this, we get electric field as kq by r square. So electrostatic force is k q1 q2 by r square. Electric field is k q by r square. In electrostatic force, there are two charges, whereas in electric field, only one charge is there. Electric field can be due to single charge, whereas electrostatic force is always due to two charges existing in the space. If there is only one charge, there is no electrostatic force, but there is electric field. Remember, whatever I'm saying, it is important. Also, we talked about this particular statement, closer together the lines of forces, stronger the field. So in this particular region, field is more stronger in comparison to in this particular region. Because here the field lines are closer, whereas here the field lines are little separated, a little far away, for sure. Similarly, here we are looking at electric field at particular point. So that's why they went like that. But if there is no charge at these points, what will happen? Electric field line will go like that. So if it is positive, it is going away from it. If it is negative, it is going into it. So remember this part as well. I'm just referring to the diagrams only. If there are parallel plates, like one is positively charged, another is negatively charged, so electric field between these two plates is going to be lie parallel to each other like that. So again, you need to remember this particular diagram as well. Lightning and lightning rod. We don't need to discuss it yet. Yeah, this particular diagram is again very important. Although we have already seen this, like point charges. If the 2 point charges are equal in magnitude, but the electric field must be going away from each other. If they are unequal, like point charges, so electric field obviously they are not going to interact, they are not going to cover, but the number of field line will actually suggest which charge is of which magnitude, like which one is bigger one. So just remember the question which I discussed in the class. It is representing the same diagram where the question says which one is bigger and what is the nature of those two charges. Something like that can be asked to you. So that's all. That's all for the given topic. That
Okay.
should be asked in your tomorrow's test. Again, try to remember and try to revise each and everything once for going to bed tonight. And if possible, tomorrow also in the morning, once you are leaving for the school, try to recollect everything by revising all these things.
Okay.
Also, this particular exercise has so many questions, so you can try some of these questions. Electric charge, electrostatic charging, electric force, conductors and electric field, till question number 18. Not till 18, at least you should try it till question number 15. Then these are conceptual questions. Conceptual questions mean those questions which actually consist of some reasons. So you can at least try to read these questions out. So remember the relation KQ1 by R square for electric field, as well as how can we actually talk about the strength. Then we already talked about how the net electric field can be calculated using superposition principle. Whenever we are solving two vectors, we are actually solving two vectors in through vector addition. We always encounter the angle as well as everything that is supposed to be there. So this is one such question, and this question is similar to what I asked you in the yesterday's class. In the yesterday's class, I simply asked you what should be the point where the net electric field is supposed to be zero existing between two charged particles. So this is the similar question. So if the net electrostatic field at any point is supposed to be zero, what you're supposed to do is you're supposed to put the value of electric field equal, which is coming out to be E1 equals to E2. So E1 can be written as KQ1 by x square, whereas E2 can be written as KQ2 by d minus x square. That is the distance from the point where the electric field is supposed to be zero. From one charge, I can assume it to be x, whereas from the other charge, it can be taken as d minus x, where d must be given in the problem. So when we solve this particular thing, we can find out the value of x, and x will give us the value of the point or the point where the net electric field is going to be zero. So we already understood this thing. Now there is another example in which we are actually finding electric field in two dimensions using vector component and superposition. So the field is existing in any plane at some angle with x or y axis. So we can actually solve field by taking the component, vector component. Always remember whichever component is along with theta is always cos component. So E must have component E cos theta in x-axis, whereas E in y direction is going to be E sine theta. So these are the components that we can actually use here. So in this particular problem, the question says, figure shows a configuration of 3 point charges. In what quadrant electric field is, in what quadrant is the electric field at the origin? The first quadrant, the second quadrant, the third quadrant. Explain your reasoning. Calculate the magnitude and direction of electric field and at the origin due to these charges. So first of all, let us try to answer the first part. So the electric field points towards negative point charge and away from point charge. Like for example, this question says, if we just try to understand that how electric field acts at origin, so in which quadrant electric field is going to be existing. Like, so if it is origin, this is positive charge, so this is negative charge. So negative charge will actually electric field terminate at negative charge. So electric field is going to exist in this particular direction. Again, if this is negative charge, electric field going to exist in this direction towards negative 5. It was positive 2. So if it is positive 2, it will going to repel electric field, or electric field will coming out of this positive 2 microcoulomb charge. If it is negative 1, electric field is going to exist in this particular direction. So net of these three electric field must lies in the first quadrant. And this is what is mentioned in this conceptual reasoning. So you can read this, and when we have to actually find out the net of these three fields, what we can do, we can simply write the values of E1, E2, and E3 by using the formula KQ1 by R1 square, KQ by R2 square, KQ2 by KQ3 by R3 square. So this is what it says: E1, E2, E3. When we add all these things, the resultant must lie in this direction, which can be written as E. So in order to find out, you can actually use all the methods. We'll find out E1, E2. Then in x-axis, E1 and E2 must be added. In y-axis, E3 is there. In the component form, you can actually write answer in this way. If you have to find out the angle, angle is going to be find out using tan. So this was my electric field. This electric field must be making some angle. This is Ex. This is Ey. So tan theta must be equals to Ey over Ex. So theta must be equals to tan inverse Ey over Ex. So you have to simply substitute the values, and calculator will give us the angle. So in this case, angle is coming out to be 30 degrees. So again, that is something you can remember and use as it is. Does this make sense?
Yeah, most
What
of
is, yeah, so what is the syllabus for the test tomorrow? Like till electric field or till Coulomb's law?
till electric field.
Electric field, is it including electric field for dipole as well, or
No,
one?
no, no,
Oh,
not dipole. Till only electric field.
okay. So electric field, electric line of forces. Now this is something that is important to remember, how we can actually sketch electric field lines. So the convenient way of graphically representing electric field is by using electric field line of forces, or called electric field lines. In order to represent it, there are a few patterns that we can directly draw. But before that, these are the properties or the rules that we actually use to draw electric field line. The first rule says the closer together the electric field line, the stronger is the electric field. Very important and very basic. At any point, the direction of electric field is tangent to the field. Like for example, if electric field is going like that, if I have to find electric field direction at this point, so we'll simply draw a tangent. At this point, again, we'll draw a tangent. At this point, again, we'll draw a tangent. The tangent at this point will give the direction of electric field on these points. So that is something you can directly remember. Third, electric field lines start at positive charge and end at negative charge. So if there is a positive charge, if there is a negative charge, electric field start from positive, go to negative like that. So these are the important properties of electric field line that might be asked to you in the test tomorrow. Then the number of lines leaving or entering the charge is proportional to the magnitude of that charge. So how many number of lines of electric field lines are coming, entering or leaving, it will depend upon the magnitude of that charge. That is again something you need to remember. The fifth one, electric field lines never cross each other. Like for example, if there are two charges, there are four charges like that. This is positive 1, this is positive 2, this is negative, this is another negative. So if the electric field exists between these charges, like from positive to negative, like that. So between these two charges, it is never going to intersect or never going to go like that. This is not going to happen, because if this point, if this thing happens, what will happen? Electric field will have two directions at the same point. So in this case, electric field might be existing like that. It will never intercross, it will never cross each other, it will never intersect each other, or two electric field lines never intersect each other. If it does, the electric field line must have directions, or must have different direction at the same point, which is always not going to be happen. So again, that is something you need to remember. So I guess this was all about the electric fields and electric field lines. And before that, what are the topic we have discovered again? You just need to remember each and everything. And in order to revise all these things through questions, I will suggest you to do some problems as well. So that there is this configuration. So electric field due to dipole. This is the diagram that can be asked in the test tomorrow. You just draw the electric field due to dipole. So again, you need to remember this. Electric field must be coming out from positive charge and entering into the negative charge like that. So this particular region has more number of electric field lines, the electric field line strength. So electric field strength at this particular region is going to be more. That is what you need to remember here. Similarly, if there is a positive conductor, positively charged conductor or positively charged straight conductor like that, so the electric field must be going like that from the conductor. Try to understand what should be the reason for these particular problems, and
Okay.
then you can answer few things. So conceptual questions as well as numericals, both are important. You need to practice them both.
Okay.
All right, then that's all for the class. In the next class, we'll be talking about Gauss law. This is going to be the last topic of this particular chapter, as per syllabus suggests, as well
Okay.
as this particular book suggests.
Okay.
Make sure that you revise each and everything.